Hello, so today we're going to start examining the second statistical test that we learned in this class, which is t-tests and z-scores. So as you remember from the chi-square week and examination, it's not standardized. So the z-score and t-test and ANOVAs are standardized, and the important numbers to know are plus or minus 1.96 on the bell curve. So, overview of hypothesis testing is a procedure that allows us to evaluate hypotheses about population parameters based on sample statistics. We use the rules of probability to make a decision regarding the null and research hypothesis. So there are one sample case t-test and a two sample case t-test. So if we were doing this by hand like you did in stats class, here's an example. A researcher wonders if the senior citizen in his sample, n equals 789, are more likely to be victimized than the population in general. Other examples are the GPAs of the student athletes different from the GPAs of the student body as a whole. And a third example is, are alcoholics treated in a rehabilitation program more reliable than workers in general? So people who are going to go on to social work or counseling, the third example is very important to you because you want to determine whether your program is working or not. And if it's not working, then you want to change your program so that you can continue to have funds coming into your program and helping people out. So we have is a difference in a one sample case between 7.2 and 6.8 statistically significant. So same or different is over the top of one of the arrows. So if the mean is 6.8, that's X bar, or X with a line over the top of it. And we have that a person in this case is 6.2. Are they same or different? So this example is coming from the population of all treated alcoholics. So here is our friend the five-step model, and as I talked about in the chi-square lecture, you want to make sure that you know the 5 steps for the final research paper that they will be asked, and they also happen for the ANOVA. So there's 5-step model for the chi-square, and a 5-step model for the t-test, and a 5-step model for the ANOVA. So step 1, you make assumptions and meeting test requirements. Step 2, which is the same as chi-square, stating the null hypothesis. Step 3, selecting the sampling distribution and establishing the critical region, which in our case is always going to be 0.05 or less. Step 4, you compute the test statistic, and again, as a reminder, in chi-square we computed the test statistic. And step 5, make a decision in interpreting the results. So here we go. In step 1 is more detail. So not only do you need to know the 5 steps, you get like half points for knowing the 5 steps, but then if you get all the steps involved in a t-test or a chi-square or ANOVA, then you get all the points. So making assumptions and meeting test requirements, we must be sure that we are using a randomly selected sample, and the level measurement for this test is interval or ratio, and we must assume that the sampling distribution is normal in shape. So for example, in the chi-square, we talked about it was nominal or ordinal measurements, and then we assumed that the sampling distribution is normal, but in a t-test, we actually look like the bell curve. So step 2, state the null hypothesis. In this class, it's always going to be there's no relationship between the independent and dependent variable. And the example that we have is a statement of no difference. In this case, the population from which the sample was drawn is no different than the sample. And the research hypothesis in this example is that we're going to have population from which the sample was drawn does not have a certain characteristic or value, and there's going to be a relationship. And also in this class, there's always going to be a relationship between independent and dependent variables. It could be increases or decreases. So step 3, we're selecting the sample distribution and establishing the critical region. We use the sampling distribution described by the standard normal curve, which is a bell curve, and a critical region of rejection, consists of the areas under the sampling distribution that include unlikely sample outcomes. The size of the critical region is reported as alpha, and the most commonly used alpha level is 0.05, which is what we're going to use in this class, which corresponds to a z of plus or minus 1.96. So basically, you can think of it on the normal bell curve. At the tails, the same spot that's 0.05 or less is also the same spot that is plus or minus 1.96. Because remember, the bell curve has a mean, median, and mode as 0 because we standardized it to all to 0. So we have probability values of the statistic obtained, the test statistic computed by converting a sample statistic such as a mean to a z-score. The formula for obtaining z varies from test to test. And you can see on the right hand side of finding critical z-scores 0.10, then the z-score is plus or minus 1.65. 0.05, which is the one we are concerned about, is plus or minus 1.96. And then as you have the alpha level p-value of 0.01 is plus or minus 2.58, and the alpha level of 0.001 plus or minus 3.29. So the p-value, as you learned in the probability lecture, the probability associated with the obtained value of z. And the alpha level is the probability in which the null hypothesis is rejected. It is customary to set alpha at the 0.05 or 0.01 or 0.001 level. In our case, we're going to use the 0.05. And again, as the p-value goes down, the z-score goes up. They're in opposite directions. So you can see the levels of significance. If alpha equals 0.05, the z-score is plus or minus 1.96, and so the tails are 2.5% or 2.5% on the left-hand side, 2.5% on the right-hand side. And where it has the shaded area, the line up to the bell curve, that is the p-value of 0.05. So again, the z-score of plus or minus 1.96 is at the same point on the bell curve as the p-value of 0.05. So these are the areas that represents the distance of plus or minus 1.96 standard deviations from a mean difference of 0, which means 2 standard deviations. These z-scores are called critical values. If we attain a z-score that exceeds 1.96 or goes up, it's bigger than 1.96, plus or minus, is called statistically significant. It leads us to reject the null hypothesis and find support for our working hypothesis. So these are the areas that represent a distance of plus or minus 2.58. Standard deviations from the mean difference of 0 is associated with more stringent 0.01 level of significance. And this suggests that these z-scores are called critical values if we obtain a z-score that exceeds 2.58. Plus or minus is called statistically significant. They lead us to reject the null hypothesis at the 0.01 level and find support for the working hypothesis. So step 4 is we're going to calculate the test statistic. In this case is the t-test. So to find the equivalent z-score for any raw score, subtract the mean of the distribution from the raw score and divide by the standard deviation of the distribution. So in this, on the exam, I give you the equation and the similar table that's on the right hand side. So community equals mu equals 7.2 days per year with 1.43, sample 6.8 days per year, and is 127. So z equals the mean, that's the x with the line above it, minus the u, mu, divided by the standard deviation, divided by the square root of n. So 6.8 minus 7.2 divided by 1.43 divided by square root of 127. That equals negative 3.15. And because you're super smart, you already know that this is statistically significant because it is way above negative 1.96. So then we make a decision and interpret the results. We need to compare the results of our z-score with the critical region. It falls within the critical region. We will decide to reject the null hypothesis, which we did in this example, and that the difference is statistically significant. So we find support for our working hypothesis related to alcoholics. If it does not fall within the shaded region, we must fail to reject the null hypothesis. The difference is not statistically significant. So then in this we have 1- and 2-tailed tests. We usually do 2-tailed hypothesis testing. So a 1-tailed hypothesis test is a hypothesis test in which the alternative is stated in such a way that the probability of making a type 1 error is entirely in one tail of a sample distribution. Right tail test, a one tail test in which the sample outcome is hypothesized to be at the right tail of the sample distribution. Left tail test, one tail test in which the sample outcome is hypothesized to be the left tail of the sampling distribution. And in this class we use the two-tailed hypothesis test, in which a region of the rejection falls equally within both tails of the sampling distribution. So, one-tailed test, useful if the direction of the difference can be predicted or the researcher is concerned only with differences in one direction. So if the researcher expects that treated alcoholics will have higher rates of not showing up than the community, you would do a one-tailed test. Type 1 and type 2 errors are if we reject the null, we have an alpha probability of making an error. Thus, over the long run, our decision to reject the null hypothesis should be correct about 95% of the time and wrong about 5% of the time. A type 1 error is only possible if we reject the null hypothesis. And the type 2 error is if we fail to reject the null hypothesis, we have a beta probability of making an error. So if we look at this, if the population, the null hypothesis is true, and when we reject, and it's an error, it's a type 1. If in the population the number hypothesis is false and we reject, that's okay. But if we fail to reject and we find support for our working hypothesis, then we made a type 2 error. So type 1 error is the probability associated with rejecting a true null hypothesis and the probability associated with failing to reject a false null hypothesis, type 2 error. So t-statistic obtained is the test statistic computed to test the null hypothesis about a population mean when the population standard deviation is unknown and is estimated using a sample standard deviation. A t-distribution is a family of curves, each determined by its degrees of freedom. It is used when the population standard deviation is unknown and a standard error is estimated from the sample standard deviation. And degrees of freedom, we saw that in chi-squared, the number of scores that are free to vary in calculating a statistic. So t-distribution, so if we have a degree of freedom which is infinity, then it's the solid green line. If it's degree of freedom of 20, it's kind of slashed, and degrees of freedom of 5, and then degrees of freedom of 1 is little dots. And as you can see, as degree of freedom of 1, it looks less like a bell curve. As you get more degrees of freedom, then you increase the shape to a normal bell curve. So here's the values of t-distribution, and we have degrees of freedom, and we want 0.05. So then we can calculate the degrees of freedom based on the different kinds of z-scores. So the five-step model again for the t-test. So we're making assumptions of meeting test requirements. The sample is selected randomly, level of measurements interval ratio, and the sample and distribution is normal. Step 2, there's no relationship between commuter students and the general student body population and academic achievement. So the working hypothesis is that there's no relationship, but the null hypothesis is that there's no relationship. A working hypothesis says that there is going to be a relationship between commuter students and academic achievement. So we select the sampling distribution and establish the critical region. Again, the sampling distribution is a t-distribution. In this example, we're going to use the alpha as 0.01, two-tailed test. Degrees of freedom is n-1, which equals 29, and the critical value for the t-test is plus or minus 2.756. So then we have the computing the test statistics. So that's a mean, which I again give you a similar kind of table. And we calculate it out. So 2.78 minus 2.50, 1.23 divided by square root of 29, and we obtain plus 1.22. Is that statistically significant? Well, no, because you know that it has to be above 2 to be statistically significant. So we fail to reject the null hypothesis. So you make a decision in interpreting the results. So you obtain the value needed to be greater than or equal to 2.756 in order to be able to reject the null hypothesis. Thus, we must fail to reject the null hypothesis. In other words, the difference between the sample mean and the population mean is not statistically significant. Also, in addition, if we had just used the alpha as 0.05, it still would not be statistically significant because it's below 1.96. So why a t-score, not a z-score? So we have used the z distribution has assumed the population standard error of the difference is known. In practice, we have to estimate it, and so we use a t-score. When n gets larger than 50, the t-distribution converges with a z-distribution, so the results would be identical regardless of whether you used a t or a z. So that's why I said in a previous lecture that typically you want 50 or more in your sample. So in most sociological studies, you will not need to worry about the distinction between Z and T. So here's the two questions that you could ask about for two sample cases. Do people living in rural communities live longer than those in urban and suburban areas? Do students from private high schools perform better in college than those from public high schools? Is the average number of years from an employer lower or higher for large firms over 100 employees compared to those with fewer than 100 employees? So the null hypothesis states that two samples have been drawn from equivalent populations. Thus, any observed differences between samples is regarded as a chance occurrence due to sampling error. Null hypothesis, for example, research statements people in rural communities live no more or less longer than those in urban communities. Actually, today, rural communities have a lower life expectancy than urban communities. Protestants have the same suicide rates as Catholics. Political conservatives and liberals discipline their children to the same extent. So we have an alternative hypothesis, or what I've been calling a working hypothesis. So if we reject the null hypothesis, we automatically accept the research hypothesis that a true population difference does exist. And this is what we hope for in social research. So here are some examples of research hypotheses. Germans differ from Americans with respect to obedience to authority. Protestants do not have the same suicide rate as Catholics. Political liberals differ from political conservative with respect to permissive child-rearing methods. Rural people lifetime mortality rates are different than urban people's mortality rates. So here's a histogram of the sampling distribution of mean differences. And again, you see that 0 because we've standardized everything. So the sample distribution of differences between means approximates a normal curve whose mean of differences between means is 0. And we calculate the differences between the two means. So the test goes as follows. The mean of 1 minus the mean of 2, the difference between the two means, and an estimated standard error of the differences. If the t-value is greater than 1.96, the difference between the means is significantly different from 0 at an alpha of 0.05 or a 95% level. So if we looked at the critical value on the table, it's higher than 1.96 with the total n is less than 122. So we're not going to worry about that in this example. So then we have t obtained represents the number of standard deviation units or standard error units that our mean difference is from the hypothesized unit value of the standard errors, assuming the null hypothesis is true. So we make assumptions in meeting test requirements. Again, the same step 1, but now we have different discussions underneath it. Independent random sample has been selected. The level of measurement is interval ratio. We know that the n of 1 is greater than 50 and the n of 2 is greater than 50. The assumption of a normal population is not required. The population variances are assumed equal. So then we have grade 1 first try of cigarettes and grade 1 tried alcohol and grade 1 tried marijuana, and we found the different means between males and females. So if the null hypothesis would be there's no relationship between males and females in trying cigarettes, alcohol, or marijuana. A working hypothesis, however, would state that there is a relationship. So we select the sample distribution and establish a critical region. So we're sampling distribution of t distribution. We have an alpha of 0.05 and two-tailed. We have degrees of freedom of n1 plus n2 minus 2, and we know that T critical is plus or minus 1.96. So we compute the testing statistics. So I, again, would potentially give you a table with the different numbers on it, and then you can compute. And we see that T attained is negative 1.25. So we know that it does not go above 1.96, whether it's positive or negative, and thus is not statistically significant. So we fail to reject the null hypothesis, and we can't find support for our working hypothesis. So we make a decision and interpret the results. Because the value we obtained was not greater than plus or minus 1.96, we cannot reject the null hypothesis of no difference. We conclude that observed differences between males and females relative to difference in grade of first-time cigarette use does not reflect a difference that would have been seen in the entire population. So now you can calculate for example, for the final exam, alcohol and marijuana, and tell me whether it's statistically significant or not. So how to do a test with SPSS. So we have independent sample t-test is appropriate for comparing the mean time spent watching TV for men and women, which is a similar example that you'll be doing in the future class. And we're comparing the means, analyzing the sample t-test. And we get out this kind of stuff. So you'll notice that the T statistic is negative 0.894 with the degrees of freedom of 477. So this automatically tells you that it's not statistically significant because it's not reaching above plus or minus 1.96. And then additionally, if you look at the SIG two-tailed column, it's 0.372, and this tells you that it has to be below 0.05. So in this case, it is above 0.05, so it's not statistically significant. So you should focus on the columns labeled T and SIG two-tailed. The t-test statistic and the SIG refers to the significance level. When we fail to reject the null hypothesis, there is no significant association between gender and TV watching. So basically, males and females watch television at about the same rate.